We've been talking about the dimensionality of physical properties of water. Now I'd like to move on to the dimensionality of some chemical properties of water and how we can use those in a way to estimate some of the physical properties of water they're related to. In particular, I want to review some of the concepts of solutions. The idea that you can dissolve solids into a liquid and talk about how much of that solids and liquid are part of that solution. And I want to talk about an example of how to apply that to estimate some unknown volume of water. So say we have water in a bucket as before, and we want to know something about how much volume of water is there, and we don't have the means to get the volume with a graduated cylinder or something like that. But what we do have is we have some salt and we have an electrical conductivity meter. I'm going to talk about how we could get to an estimate of a volume with those devices based on knowing something about solutions. So just some of the language of solutions. You're going to have a solute, or the stuff that is dissolved. In this case, we want to use sodium chloride. We'll talk about sodium chloride. It's a really common hydrologic tracer because it tends to behave conservatively. The sodium and the chloride don't react with things once they're dissolved in the water. In our case, the solvent is water. And sodium and chloride tend to completely dissociate. The ions tend to completely dissociate in water because water is a polar molecule, and water is very good at surrounding things with a charge based on the charged ends of the water molecule. This polar characteristic of the water molecule makes it what we call a nearly universal solvent. So other than some of the organic molecules that don't have a charge on them, water is very good at dissolving things. And sodium chloride, for example, is extremely soluble in water. It's remarkable just how much mass of sodium and chloride you can get dissolved in water. So the way we quantify concentrations is with a variable that we might call C of a solution here, or the concentration of a solution. And dimensionally speaking, we can derive what the dimensions of that concentration would be from how we do the calculation with other variables. So one of the ways to characterize a concentration of a solution is to take the mass of the solute and divide that by the volume of the total solution it's dissolved in. So dimensionally speaking, we've got the fundamental dimensions of mass in the numerator, and we've got a volume in the denominator, which we've talked about as being a length cubed. So we have a mass per length cubed here for our dimensions of a concentration. Now there are other dimensions that you can use for concentration, but this is the one we're going to focus on. Now, when we dissolve things into water, it tends to change some of the physical properties of the water. And one of the properties that putting salt into water will change is electrical conductivity. The electrical conductivity of water tends to be very sensitive to how much chloride is dissolved in the water. So that gives us a property of the water that we can measure to make an inference of how much salt might be dissolved in the water. And using that measurement of this solution, the concentration of the solution, might give us a way to estimate the volume of a solution if we know how much mass of the solute we put into that solution. While we're discussing concentration, it gives us a good opportunity to recognize that dimensions are abstract and they don't necessarily tell you everything about a variable. For example, concentration might be provided in several different dimensions. A really common dimension for concentration is molarity, or moles per volume of solution. Moles are a count of molecules based on Avogadro's number, and we specify a count or a number of things using the capital N in dimensional analysis. So molarity would be the N per volume, or the number of molecules per volume of solution. Molality is similar, but it's the number of molecules per mass of the solvent, not the solution, but the solvent. Also, we might specify concentration as something by percent by volume. So alcohol is typically characterized like this. If you get a can of beer, it's going to give you the amount of alcohol by a percent by volume. That's the percent of alcohol relative to the total volume. Also, mass per volume is not always a concentration. It matters whether you're talking about mass of what and volume of what. Mass could be the mass of stuff per volume of that same stuff, in which case that would be the dimensions of density. So mass per volume as a concentration appears to have the same dimensions of mass per volume as a density. Now, the key here is to recognize that context is everything. The context of the dimension matters. The mass of what and the volume of what will tell you what you really mean by a mass per volume and whether you mean something like density or concentration. So just a quick reminder that dimensions are extremely useful, but they're also quite abstract, and you have to have a little bit more context to understand what they mean.